recording?
It's beeping red.
Is it flashing red?
Yeah.
That probably means it's recording.
Okay, it's recording.
Good. What I want to talk about today is this thing called Newton's method. This is actually kind of exciting. Thank you. Alright, classic calculus topic. This is actually in chapter 3, which I think makes no sense, because in my opinion it is an application of linearization. And Newton's method rests on the assumption that most functions are kind of normal. Most functions are predictable. Most functions, you can tell what the function is going to do next. And what is the thing which kind of tells you what the function is going to do next? The derivative, yeah. The derivative of the function tells you what the function is about to do. It also kind of tells you what the function just did, because, like, you know. Okay. So, here is the idea. Okay, big picture coming. I mean, like, I'm going to draw a big picture, so should you. Alright. And, yeah, we have a function. And let's suppose that this function is kind of coming in a little bit like that. That could be better. Should I redraw it or just go with it? I think I'll just go with it. Okay. So, here's the function. Let's call this function f. And the idea is, Newton's method is used for one thing, and that is to find the roots of a function. So this is a function, and I would like to know when it is 0. Oh, by the way, this this lesson or this method is assumed to be a method like that you do if you do not have a calculator. So this is kind of, either you can think of this as some 400-year-old thing, which it is, or you can think of it as something you would do if you were trapped at a desert island and needed to, like, you know, calculate engineering coconut-based submarine that you're building to very high levels of accuracy, and you do not have electronic devices. Or, more realistically, learning about Newton's method for you kind of guys, because you're like smart and stuff, is something that you need to know how to do by hand, because it is the justification for how the calculator does things. So this is actually going to be one of those, oh, this is how calculators work day.
Have we had one of those before?
I don't think so, not really.
So in first semester with linear algebra, sort of ish.
Oh yeah.
Yeah, to some extent, right. How do calculators solve a system of equations? We know how to do that by hand, but then we use the calculator to do it for us subsequently. So this is the same kind of thing. Okay, so I would like to know what this root is right here, and I do not know. So maybe I'll just put like a dot or something, and I'll just write like root question mark. So I would like to know, to any desired degree of accuracy, where this function crosses the x-axis. Okay, well, there is a recursive procedure, and the recursive procedure goes like this. First, I guess. I guess what the root might be. And let's just say that my initial guess is way up here. Picture not to scale. This could be like pretty close, actually, right? So let's call my first guess x1. In other words, I pick an x value and say, I wonder if that is a root. Well, I have a formula for the function, so I can plug any particular number in and I can see if it works. So I plug in x1, and what happens? Well, unfortunately, it's not 0, which is what I was hoping. Right? So it's not the greatest guess. Okay, well, the thing is, even though it's not the greatest guess, what I will now do is I will construct the tangent line to the curve. And this assumes that this function is differentiable and everything, right? I will construct the tangent line to the curve at this point x1 because, after all, the tangent line to the curve is a pretty decent approximation of the curve, at least near that point. So watch this. This is like a brilliant idea. So I construct the tangent line to the curve. And I would say, all right, well, if this function is pretty close to its tangent line, as long as I stay pretty close to x1, then it might be hard for me to find the place where the function crosses the x-axis, but I can find the place where the tangent line crosses the x-axis. And so let's just do that. So I calculate where the tangent line crosses the x-axis, and I hope that that is the root of the function. But it isn't, right? So I plug in x2, and when I plug in x2, I get a point which is, however, better. Yeah, Daniel Chen's having a moment. Now, was that 0? No, it wasn't, so I just do it again. I construct the tangent line to the curve at point x2, and then, again, as these two are pretty close to each other, they should have roughly the same root. And so I get x3. Is x3 right? Well, no, not exactly. But if I plug x3 into the function, and then I construct the tangent line to the curve at x3, are you guys seeing what's happening here? At least according to my hand-drawn, fake made-up diagram, I'm going to quickly converge on the true root of the function. It's pretty beautiful. Okay, so this is Newton's method. This is a recursive procedure in which you estimate the roots of a function by constructing tangent lines to iterated guesses.
But it's never going to give you the exact.
It's never going to give you exact. You do it until your coconut submarine is accurate enough. Coconut-based submarine. As soon as you have it up to 3 decimal places or whatever, then you say, okay, we're good to go. Then you send someone else.
Wrong decimal places.
What?
What if the 3 decimal places are wrong?
Okay. No. What? Okay. So, for example, suppose I would like to know what the square root of 3 is. So I would like, what I'm looking for now is a decimal approximation of the square root of 3. Okay, well, I know it's like 1.73 because I think I memorized that, but this is exactly the kind of thing that we're going to figure out. All right, so now what you must do is, using your imagination or whatever, can you think of a function, and by the way, built into the notion of this algorithm is the idea that my function f should be one for which I can compute the values by hand, right? Because the part of this process was plugging numbers into the function, so I should be able to do that, right? So can you think of a function which has a root at root 3?
I mean, x squared.
Yeah, x squared minus 3. Yeah, he says, of course I can. Let's just take the simple function, x squared minus 3. I know everything about that function. I know what it looks like. And indeed, this function, if we graph it, so this is just the function which has been moved down 3. And just like, duh, what is one of the roots of this function? One of the roots of this function is root 3, right? And what's so great about this choice is that for any number whatsoever, as long as it's like, not crazy, I can square it and subtract 3. That's something I can do. And I also need to be able to take derivatives. So what's the derivative of this function? Yeah, it's just 2x. Okay, so now what we're going to do is we're going to make a giant chart. Kendra, can you make sure the camera's on? And if Dawson's head is in the way, please tell them to scoot down a little bit. Okay, so what we're going to do is, because it's a recursive procedure, we're going to make a big chart.
Arlo, you have to move your head.
Okay.
And Dawson has to move.
So what I'm going to do is we're going to make a big chart. And let's go through. What are all the things? So I'm going to start with the first guess. Oh, can anyone think of a good guess? Like, give me like what is the square root of 3 close to integer-wise? 2. Thank you. So my first guess is just going to be 2. Seems pretty instant enough. All right. What's the next thing I'm supposed to do if I'm guessing 2? What's the first thing I should do? Plug it in and see if it works. So I'll make a little column for the y coordinate. So I plug in 2 and I get 1. Okay, which is pretty close to 0, but like not close enough. What's the next thing I want to do? Since it didn't work, or since it didn't give me exactly 0, what should I do next? Find the derivative at 2 so that it can construct the tangent line, right? Okay, let's do that. What is f prime of 2? 4. Yeah. So thus the slope of the tangent line to the curve is 4. Okay, and I can use the slope of the tangent line to the curve to, what should I do next? Yeah, I can just like make the tangent line, right? Okay, so what is the tangent line to the x squared minus 3 function at the point 2, 1?
Y minus 1.
Yeah. That's not so hard, right? Y minus 1 equals 4x minus 2. Okay, and now we have to do a little bit of algebra 1. What's the next thing left? What's the next thing we're supposed to do in the algorithm?
Find out when that's 0.
Find out when that's 0, right? So find the x-intercept of this line. And okay, so I want, that's kind of what I want, right? The x-intercept of the tangent line. That is correct. Yeah, this one's easy enough that you can kind of do it in your head. should we just generally like talk about what's the simplest way to do this? I guess we just set y equal to 0 and then just solve for x, right? Yeah. So if you did the most kind of like efficient way to do it is, well, you take that guy, so you have -1 equals 4, x minus 2, and then you just like divide by 4, and then you just like add 2. So you do 2 minus 4 is 7/4. Okay, so that means that the tangent line to the function at the point 2, 1 intersects the x-axis at 7/4, and what do I do at that point 7/4? Yep, you do it again. 7/4 now becomes the seed for another application of this whole thing. Okay, so should we do this like semi together, or do you want to just do the rest of this line by yourself? Yeah, just go. That's pretty close to 0, so like already we're doing pretty good. Cool.
Oh no, I'm thinking 30.
Yeah, I told you that we were going to do a thing with like true. Okay, and now you just have to solve this little thing, which is kind of like algebraic, or it's arithmetically kind of annoying, but not actually that hard. Did you do it already? So you get like, I want to multiply by 2 7, so you get like -8 over.
What?
Try that again.
1 over 56.
7, what, -1 over 56. Nice, Kindle.
No problem.
Equals x minus 7/4. So it's just going to be like, yeah, it's going to be 7/4 minus 1 over 56. What's that? Like 1670 what? Hold on, let me try that again. Is it 16? Yeah, 16. 16 times 7, 70 and 42, 102, right? Oh no, wait, what did I just do? How am I doing? Oh yeah, I should multiply by
14.
Whoa, 14. Yeah, 14.
So 7 times 14 is
78.
72.
Yeah, so it's 97 over 56. Yeah, good. Good. 97 over 56. Okay. So and then
we're not doing it again, are we?
No, we're not going to, but we're going to like say that we could do it again if we wanted to, right? But then the amount of time this takes gets harder and harder. But you could go for a couple, and this is quite it's quite incredible. If you type 9756 in your calculator, you will see that it is very close to square root of 3. It's like pretty impressive. Okay, last thing. Oh man, I kind of ran out of room. Let me just erase some of this. So the last thing is. And this sort of seems, okay, well anyway, this is the understanding way of doing it. This is how I'm going to make you do it on a test. But there is like a fast cut, shortcut it's called sometimes. Let's just do this, process in general. If we do this process, if we just kind of go through this process in general, and sort of think about what we're doing. So equation of the tangent line, and then this is x-intercept, etc. Okay, so this is like, so essentially we start with, let's call it x1, and then when we take f of that, we get f of x1, and then f prime, well, that would be just like f prime of x1, not really doing anything here. And then what would the equation of the tangent line be?
Y minus f of x1 to f prime of x1 times x.
Yeah, Kendall, did you move the camera?
It's still in view.
Okay, good. Liar. All right, and then we will trust issues. Okay, then
No chill.
What is the x-intercept of that line? So can we just do this? So if we just, what's the process is we just set y equal to 0, then we get like negative f of x1 equals f prime of x1 x minus x1. You guys following this? It's the exact same thing, just like in general. So now I just need to solve for x, right? I set y equal to 0. Is this cool? Y equal? So just we do some thingies. What should we do? I guess we just divide by f prime of x1. And then we get x minus x1. And then we just add that, right? Are you satisfied with this?
So satisfied.
That's so weird.
So, that was a callback. Something that happened last semester, right? Yeah. Okay. So, what goes here? What is the x-intercept? It turns out it's x1 minus f of x1 over f prime of x1. And of course, what do I do with that? You just make that x2. In other words, Gina, I think I can come up with a recursive formula. Could somebody please tell me, in general, what x sub I plus 1 is? You guys following this? Or did I do it?
Oh, it's just x1, it's that.
It's just like that, basically, right? X sub I plus 1 is, Dan Jacobson?
x1 minus f of
xi.
Or xi. Yeah, xi minus f of xi over f prime of xi.
Yeah. And so this is kind of like the dumbed down version of Newton's method, just encapsulates the recursive rule, sort of takes the whole chart and converts it into just a little recursive formula from which we may just like very, very quickly get the next number. Okay, so suppose I wanted to do this really fast. I could do a thing right now. Watch this. So, camera over here. So, since that's my recursive formula, maybe you guys don't know how to do this. Although Giles taught me, but my experience is that you all forget. If you go into y1, I should type the function, which is x squared minus 3. So, I know. X squared minus 3. Looking good. And also I need to be able to crank out some derivatives every now and then. So I'll put 2x in there too. Now you might be having a weird issue here, which is, Ms. Rose, didn't you just tell me that this is the whole point of Newton's method is that you don't have a calculator? Yes. But the other point of Newton's method is to program your calculator to do things like find roots. So it's not totally ridiculous. Right? We're just I'm doing things on the calculator which in principle I could do by hand. Okay, good. So those are my functions, and then essentially what I want to do is, well, I'm going to start with the seed of 2, right? So I just go 2, enter, and then well, according to all this math I just did, how do I get the next number? That formula, in other words.
Answer minus.
Answer, yeah, Sam's on the ball. The next number should be the previous number. Minus. F of the previous number, right? In other words. Yeah, y1 of the answer. Do you guys remember this? You go bars, y bars, function, y1.
Oh god.
of the answer.
Completely forgot.
Remember the existence of this functionality? If not, this is what school is for. And then divided by, what am I supposed to divide by? The derivative, which is y2. So you hit vars, y bars, function, y2 of the answer. And that is an expression which should, bam, give us 1.75, that's 7/4. Yeah? Okay, cool. What if I hit it again? What am I going to get? Hopefully I'm going to get 97. What happened? Yeah, that's right, right? Because you can just keep hitting enter over and over again because it just answer just what?
It's correct for 3 decimal places.
Yeah, and that's correct.
It's a score of 3.003.
Yeah, that's like good. Sam is saying that's good. And I'll just keep doing this. Boom, 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 boom. And within like a couple of, like, look at how good this is, right? I've already within, I can't stop counting, but I think it was about 5. I have exhausted the number of decimal places that my calculator will display. So this is an extremely fast, the rate at which this algorithm converges on the true answer is like very, very good. That is root 3 accurate to like 8 decimal places or whatever. Okay, are you impressed?
Yeah.
There was something else I was going to say about this. Oh yeah, this is not actually correct, but it's like a white lie, that this is how your calculator finds the roots of functions. Remember that whole thing when, like, suppose I want to know where, suppose I want to know when the x squared minus 3 function intersects like 2 to the x or something like that. Sort of a bad example in some ways. Oh yeah, let's make that, okay, no, here, let's do this. Suppose I want to know when x squared, what would be a hard function? Like, how about like insert, you know, x to the 5th plus, okay, that's like a, new calculators. Okay, yeah, x to the 5th plus x squared minus, okay, that would be a function which hopefully doesn't have rational roots, does it? No, good. So, that would be a function that would be really hard to find the roots of, like borderline impossible. But, as you are probably aware, if I graph this function, it has a root. Is that a root? 1? I hope not. No, it's not. It's close to 1 though. So you know how your calculator has this functionality in which you go second calc into, hey calculator, what's the 0 of this function? And then it says, all right, I'm going to search within some interval. So you hit enter. And then you go move your cursor over and you're like, hey man, where's the right bound of this function? You hit enter. And then it says guess. Remember this thing you probably always wondered, hey, why are you making me guess? What's wrong with you, calculator? Guess is sort of the seed to a Newton's method-like algorithm, which then goes boop, 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 and then tells you that it's 1.1. So it's basically calculus that the calculator uses to approximate things. There's lots of calculus going on in all kinds of like numerical approximation functions. All right, Gabe.
How do you make your own guess? Or how does the calculator like decide on a guess?
It doesn't. That's why it's forcing you to prompt.
No, but like if it needs to, if it's finding the square root of something.
Probably. Oh, if it's finding the square root of something, it uses a different thing.
Okay, but like in general, what if you wanna have a guess? How do you find a guess without looking at a graph? Like a standardized guess.
Did you say you weren't going to call on Gabe?
No, I don't know, man. I mean, the square root of n has to be less than n, so how about that? I don't know, take n over 2 or something, start from there. I mean, whatever. There's like ways. There are ways. There's a whole class, theoretically, called computational methods. If you're crazy, you'll take at FAM teaches where you learn about these kinds of things. Okay, good. That was way too long. We have 15 minutes. Here's what we will do in this last 15 minutes. We will go over the homework on anti-differentiation, which I'm willing to spend anywhere between 1 and 4 minutes on, because I thought it was pretty chill. And then I would like to devote the last 10 minutes to going over some applications of different... I think we can stop this, actually, also.
Yeah.
Yeah, turn that off.